This presentation is on breadboarding and electronic components. So we've been talking about using breadboards in class, and I guess we need to define finally, now that we have them, what is a breadboard. Sometimes a breadboard is called a proto board, but it's a reusable platform for temporarily built electronic circuits. It's a way to easily put together circuits that perhaps you've drawn for some purpose, and it's just checking to see if the circuit does what you want it to do. It's a very easy way to put it all together. This is a diagram of a breadboard here, and as you can see, it is really just a collection of individual little holes, and wires will go in these holes. It's also very similar to the CPO circuit board that you've been working with that has the posts, except instead of having posts that you connect to, you're going to put a conductor into the wells on this plate, and there are connections inside the plate. So why do breadboarding? Usually it takes less time and money, the breadboards are reusable of course, to breadboard a circuit than to design and fabricate a printed circuit board. This is especially true if we're talking about microelectronics. So we can test the circuit without having to go through the process of a printed circuit board. Because of the cost, a PCB should be reserved for the final working design. So once you have the design tested with breadboard, then you would go through the process of generating the PCB. As a complement to circuit simulation also, breadboarding allows designers to observe how and if the actual circuit functions. So as I've said several times, it's a method of testing a circuit. So on the breadboard, electric components are going to be placed, the leads from them, the wires from them, are inserted into holes that are arranged in a grid pattern on the surface, and a series of internal metal strips connect the rows and holes. And you can see here that we've got strips running in this direction and also in this direction horizontally. Columns and rows are connected, so we have, as you can see, the positive strip here. We then have rows across, directly across, and then across over here. This is not a connection here, so actually this side, the A through E, is disconnected from F through J, and to actually connect those two sides you would have to run a wire across to do so. These are holes to insert the wires. You will not just have one wire going into a hole usually. And we use jumper wires, which would be like this, as rarely as possible if we can. But we use as few jumper wires as possible. Internal breadboards make the strips and should make the majority of the connections. So we let the internal structure of the breadboard make the circuitry whenever we can. So keep jumper wires as short as possible to avoid jumbled wires which are difficult to troubleshoot, such as this. This is a much better looking arrangement where everything's nice and tightly arranged. So some guidelines and tips whenever you're breadboarding a circuit. Generally you should have a circuit diagram first, a schematic that shows how things are connected. And you want to breadboard the circuit closely to the layout of the schematic circuit to aid in troubleshooting. You want to use the schematic and check off components and wires as added to the breadboard to make sure you didn't miss anything. And then you also cut component leads to short lengths so that you can avoid contacts and shorts between them. And if something goes wrong and you don't see it, have someone check the circuit for errors. One of the components that we will be using in class to help us visualize if the circuit's working or not are lights known as diodes. Diodes allow current to flow in only one direction, and we have a negative lead here and we have a positive lead there. So you have to make sure that the longer wire is on the positive side of the circuit and the shorter wire is the negative. And in a schematic, this is the symbol for a for a diode, with this being the positive side, this being the negative side. So you can think of this as an arrow pointing to the negative side. Resistors tend to have this symbol, or something very similar to it. Resistor is an electronic component that resists the flow of electrical current. Resistors are typically used to control the amount of current that's flowing in a circuit, and resistance is measured in units of ohms, named after George Ohm, who developed Ohm's law, which you've already seen in another video, and that defines the fundamental relationship between voltage, current, and resistance. And you can see these barrel-shaped objects are our most common resistors with colored bands on them. There are various types of resistors, however. Carbon film resistors can be of a couple of different types, but these are the symbols that are used for them in circuits. A variable resistor, or a potentiometer, which you have some experience with the CPO kits, and that's going to have this symbol. And then we have surface-mounted resistors, which are going to have the same as the carbon film resistors. So how do you determine a resistor's value? Resistors' values are color-coded. Resistors are labeled with colored bands that specify the resistor's nominal value. Nominal, when you see that term, that would be a numerical value. Nominal actually means name. So if we have a certain color coding system, a certain series of colors, we're going to end up saying that the numerical value will name that resistor based on the number of ohms that it has. The nominal value is the resistor's face value. And we measure that with a digital multimeter, and the digital multimeter can measure the resistor's actual resistance value. Okay, so the resistance color code. There's a couple of different color coding systems. One is a 4-band and one is a 5-band. We're looking at the 4-band system here. We've got a first band, second band, third band, and then there's a separation and a 4th band. The first band is the first digit, the second band is the second digit, the third band is a multiplier, which multiplies this times a value, and then we have the tolerance, which is, this one particular one is 6%. So you can see over here we have various colors, and we would start with first band, second band, multiplier, tolerance. First band, second band, multiplier, tolerance. Or actually this would be first band, second band, third band, tolerance. It's going to go in the other direction, I believe. Alright, so let's do some examples of that. Let's determine the nominal value of the resistor shown. So we've got first band is brown, second band is black, so first band, brown. We'll actually see this come up a little bit later. Second band, black. Third band is the multiplier down here, and then we've got a tolerance in the 5% range. So as you're reading this, first digit is 1, second digit is 0. We're multiplying by 100, and then that's plus or minus a tolerance of 5%. So 10 times 100 is 1,000, so this would be 1,000 ohms. As you can see here, 1,000 ohms plus or minus 5%. And since 1,000, the prefix for 1,000 is kilo, we could also say that this is 1 kilo ohm plus or minus a 5% error on either side. Let's determine this one. We have orange here, we have white here, we have a multiplier that's green, and then we have a tolerance, again, of 5%. Okay, so that gives us 39 times 100,000. Okay, 100K would be 100,000. So that's going to be 39 times 100,000. Separate these. It's going to be 3.9 million ohms, plus or minus 5%, and the metric prefix for million is mega, so this would be a 3.9 mega ohm resistor. All right, so let's look at this one. We want to determine the color bands that should go here. This is a 1,500, 1.5 kilo ohms, so that's 1,500 plus or minus 5%. So this becomes 1,500 ohms plus or minus 5%. So our first digit is 1, our second digit is 5, and then we're going to multiply that by 100, so that would be red. Okay, so that's 1.5 would be 15 times 100 would be 1,500, and we've got a 5% tolerance that's going to be gold. So our colors should be brown, green, red, and a 5% tolerance gold. And this particular coloring down here, at least on my computer, does not show up very well as this particular resistor. All right. Measuring resistance, as you've already had quite a bit of experience, we use a digital multimeter to measure resistance, and we'll want to make sure that we're using that properly. And that is the end of the presentation. We'll have more practice on measuring resistance as well as Ohm's law very soon.